Hello guys, welcome back to the YouTube channel of The Concept Guy. And first of all, I want to say that everyone please remain in your homes, okay, so that we actually fight with this coronavirus that is spreading rapidly in these days. So please stay at your homes and just keep social distancing around, and I hope it will help us to eliminate this virus. So next we have here a question, the third question of Azeotropy 2020, and it is a symposium of I.I.T Bombay, as you can see. And we have the third question of Chem Eng, and here the question says that we could consider a spherical porous catalyst. Okay, so there's a spherical porous catalyst in which the reaction A to B occurs, and that's a first order reaction, and we have C0 is 1 molar, and we need to find concentration of A at R is 0.4 mm and R at 0.7 mm. So you could actually go through the question, pause the video and go through the question, and then we see that here we Thiel modulus is given as 2, and radius of catalyst particle, the overall radius of catalyst particle is 1 millimeter. We want to find at a particular radius, like a particular distance from the center of the sphere. Okay, so total is 1. We want at 0.4 and 0.7 the concentration. Okay, so if we move to Fogler, it's called Fogler's book of elements of chemical reaction engineering. So in the chapter of diffusion and reaction, okay, so we find out that the derivation and of the differential equation that describes in a sphere is given. So we could actually go through this. That is my sphere. This is a particular r radius, and at a particular, we consider a shell at r plus r, a small r radius, and at that distance we consider this to be a shell, and we do a mass balance. So this is a molar balance here, rate in, rate out, and you can actually find out that after all these steps we finally arrive at our equation kind of this. So because we have a first order reaction, so we will move to this equation. Okay, so this is my final equation that I get after the whole derivation. Go through it. It is very simple because there is just molar balance of diffusion and the gradient is taken, and so here some terms need to be understood, that this thing, this variable, I call it psi. So this psi variable, okay, is Ca by Cas. Okay, so we want to make it dimensionless because that's easier to evaluate. So psi is Ca by Cas. So what is Cas? Cas is the concentration at the surface. So at r is small r is equal to capital R. This is the surface of the sphere concentration, and lambda is r by r. Okay, small r by r. So we found out that our equation comes out to be somewhat like this, but for first order reaction it is kind of this equation, and with our boundary conditions that psi is 1 at lambda is 1 and psi is finite at lambda is equal to 0. Lambda is r by r, small r by capital R, and psi is Ca by Cas. Okay, so at the surface, at the outer surface, when lambda is 1, that means small r is equal to capital R. So at the outer surface of the sphere, the concentration Ca is Cas because psi is 1. Okay, so now what we see that we need to solve this in MATLAB so that we can get to a certain psi versus lambda equation. Okay, so the it's called Fogler has already solved it, and they have arrived to this equation. Okay, this is our analytical solution. So we will just quickly see what it is to be done in MATLAB. Okay, so our question here, we have this question, remember this, and this is our analytical solution. We move to MATLAB. I've already written out the codes because it really takes a lot of time to actually get it in a proper manner, and I have actually added these comments that are in green so that we understand what is to be done, what codes means what. Okay, so first we plot the analytical solution. Okay, not the solution that we get from MATLAB, but we plot this solution. Okay, this Ca by Cs. So my psi SHI, okay, psi true is, okay, so I am denoting lambda by LAM. Okay, this LAM, lambda. So my phi is 2. My lambda values are from 0 to 0.1, 0.2 in steps of 0.1 till 1. Okay, so 0 to 1, that's my range. Okay, and in step sizes of 0.1, and then we see that for all these lambdas we put in here, and we get a corresponding psi values. So psi true, that is from the analytical solution, I've written the same formula that I have used here. This is the analytical equation, and I have plotted the psi versus lambda, and I have put the hold on so that my plot is held while I do the same thing with using numerical methods in MATLAB. So this is important because analytical solution is more of pen paper work, but MATLAB thing is numerical methods. So we'll get to that. And so from this, we first need to remember that we are using this 23 line is our main thing. Okay, for that we have written erased everything, but this 23 line is using of BVP4C, that is an inbuilt MATLAB function that helps us with boundary value problems. Okay, so boundary value problems, BVP4C. Fourth is the fourth order, so we will not get much into it, but we will see how we can use it to solve boundary value problems. Okay, so first it needs, so let's take help I'm asking MATLAB for help to help me with VVP 4C. Okay, so you can actually go through this. It's coming busy here. Okay, so right now it's here, so you can actually go read this. First we need an ODE function, then BC function, then solinit. Okay, so my first function is @chem3. That is my ODE function. So I will move to the function, and here in this function you can see that fval, I need to extract out fval. That is quite similar to what we have done in ODE45 case, that this function returns the derivative of first my y, and my the second element is the derivative of my double derivative. It's like double derivative of y means derivative or first derivative of my derivative. So let's say dy by dx is y2 and y1 is y. So it means y has two elements, one y and the second is dy by dx. Then if we say y, if we take derivative of both of them, then this will become y2. Okay, because y2 is dy by dx. So dy by dx. And the second thing here is a little, you might not get confused here. I've written here is that, so let's move on to this equation. So here you see that my second derivative is minus, if you put a whole of this to the right hand side, because we want the second derivative, then it is minus 2 by lambda d psi by d lambda plus psi into TL modulus square. Okay, so we see that this psi into square. So as you can see, when lambda is 0, so this d square psi by d lambda square would actually become kind of infinite, and it's really difficult to find this term because 1 by 0 would be actually infinite. Okay, so that could arise a problem in numerical methods, because in numerical methods infinite is really, we cannot help it. So we need to actually define it as a vector of S. Okay, so I went to MATLAB help center. Okay, so I went to MATLAB help center, and here what I got is that to solve BVP, that boundary value problems with a singular term, where this kind of situation arises, that the y double prime plus 2 by x into y prime plus y5 or some function of y is 0, then we can actually have it in this term. So where my S is, S accounts for that matrix that is creating the problem in singularity. You might refer to this MATLAB help center page with solve BVP with singular term and look into it how they have done. But for now, what we have seen is that they have made it really simple, that my S is a matrix that is creating a problem. That means because it is multiplied with 1 by x, so my x will be 0 and that will create a problem. So I have to evaluate it separately. How we do with that, we will see that in MATLAB. So note that dy will double derivative of y with x is this. Okay, we neglect the term. What term do we neglect? This term, because this term is creating problem. So my d square psi by d lambda square is nothing but equal to, this goes that side, so that is because my TL modulus is 2, so here it becomes 4 into psi. So I have denoted here psi with y. Okay, psi with y, and my x is lambda. Okay, so remember that psi is y and x is lambda. Y contains two elements. First element is y itself, and the second element is dy by dx, as we see this. So this is clear, I guess. So the next function is @chem3bc. So this function is actually gives us the boundary values. Like here, a and b are set. So a is x is equal to 0, and the when the center of the sphere, and b is the surface of the sphere, x is equal to 1, and x is, again I'm saying, it's lambda. Okay, and y is psi. Okay, so dy by dx is 0 at, this is my first boundary condition and this is my second boundary condition. So I put in the boundary conditions. Then what I've done is I have made a solinit, because I need a solinit mesh, that with respect to this mesh I need to evaluate using these two functions and get my solution. So this solinit will create a basic initial mesh. Okay, so x low and x high, I've put it that 0 and 1, and in a mesh size of 1000, and with these initial conditions that my y, let it be 1 initially, okay, and a constant initial guess, and 0, my dy by dx, let it be 0, my constant initial guess. Okay, somewhat. So now I will put this S vector and solinate, this is BVP. I've said this, that initial guesses x low 0 to 1, solinate BVP I init. Okay, BVP init, that is a inbuilt function of MATLAB that gives us the initial the sol in it, like the solution initial. Okay, the initial solution mesh. So this is a one row and multiple columns vector. Okay, and I've put this S as 0 0 0 minus 2, because as you can see that here my S is 0 0 minus 2, because it was somewhat of this order, y2 prime is equal to minus 2 by x, y2 minus some function of y. And here also I have somewhat that thing, because this goes that side, so it is minus 2 by lambda and the psi by d lambda plus 4 psi. Okay, so I have this as my singular term, remember. And finally I have s, and I put options is equal to bv set, so I need to set this singular term s, and singular term set you can actually go to help and bvp set and get to know what I'm actually doing here. Okay, so then I finally get a solution that takes in account the ODE function. So bvp foresee ODE function, the boundary conditions, first the function, the function carrying the derivatives, then boundary conditions, then the initial solution mesh, and my options. So options is basically to put this singularity thing, and then I just plot my results, sol.x and sol.y1. Sol.x is my x values, okay, and that are from x low to x high, and in steps of 1000, like there are 1000 actually row columns actually. Then finally with respect to sol.y first, because we want psi and not d psi by dt, and all the columns. So when I just run it, I get this kind of figure from lambda is equal to 0 to lambda is equal to 1. See, there is an overlapping of two plots, one red and one blue, because my analytical solution has hole in it, and so my plot, this plot and this plot are both plotted on the same graph. And I see from 0 to 1 my analytical solution and my MATLAB solution are both lying on the same. So we are getting a good response, okay, with very less error. Now we see what the real answer is. So from this you can actually get the real answer, and that to be like from this graph we get this answers, okay, at 0.4 mm and at 0.7 mm. Hope you like the video. Please like, share and subscribe.